so let's see, second half of the recording. Okay. For the question that we just did, you could also do it using the form language, which I have in purple here. Again, you'll need to parameterize. We write our one form, we plug in the parameterization into our one form, and we also dot it with our derivative of the parameterization. So it's just same answer using different language. Okay. Let me think. Was there something? I believe which question? Okay, that's something else. Okay, any questions on Stokes' theorem then before we do Gauss's theorem? Yes.
I have a question about office hours for this class. Like after like the classes end and it's like into like the days and stuff, like are the office hours gonna be like not the same?
Yeah, I think there are no more I think office hours just stop, but I'll still have office hours.
Okay, like so if you need help like doing something, then we can go to your next like
yeah. I mean some TAs might be holding extra office hours. I'm not too sure about that. But yeah, I'll let you know if like they say something to us. Yeah. I might send out, maybe I'll send out like or I'll do it based on the when to meet for the final review session to pick what office hours I'll add. Okay, so divergence theorem or Gauss's theorem. So recall that divergence is you're adding the partials of each component. So I just wrote that to recall. What is divergence or Gauss's theorem saying? So it's saying that to find the outward flux of F across S, you're going to do, this is what you want to find on the left side. So always remember that Stokes and Gauss's theorem is an equality. So you need to write both sides of the equality. You can't just say Gauss equals right side. Okay, so if we want to compute this left side, sometimes this left side, that's too hard to compute. So instead, we can do the triple integral of our like object, and the integrand will be the divergence. In one form language, you would have the integral of this two form is the integral of the derivative of the two form. And so how do you know when to use Gauss's theorem? So if it says like, what is the flux out of the closed surface? So like it says like out of some surface or like, yeah, then you want to use Gauss's theorem. If it says something like find the flux of the curl, that language is telling you to not use Gauss's theorem. You should use probably Stokes' theorem if it says flux of the curl. Okay, so let's do an example. So here, yes. If the question says find the flux of the curl of F, you want to use Stokes' theorem instead of and not Gauss's theorem. Because Gauss's theorem is usually for finding like the outward flux of some vector field only. But here it says like flux of the curl, not of some like a specific vector field. This is saying flux of the curl of F. So if it says something like this, you should use Stokes' theorem instead for the second one. And specifically for Gauss's theorem, you also want to make sure that your surface is going to be closed. And so, yes. So like, for example, if your shape was just the top of this paraboloid, like if this was just your shape, then you can't use divergence or Gauss theorem because your shape should be closed. So in order to use Gauss's theorem for this, you would have to add this lid so that you have an entire closed shape. Then you can use Gauss's theorem. But if you didn't have this like bottom part and it's just like an open paraboloid, then you can't use Gauss's theorem. Yes.
So when you say add the lid, so we would compute.
So it would be like, so say we add this surface, then the divergence, you could do the divergence over this whole solid shape now. So you get some answers. So like flux over your total, like this total shape.
And that would be
flux-
using the, like, which side, the one that uses the boundary, because if you use the boundary, then you can use that circle, you know what I'm saying?
Do this side.
Over
This.
the entire.
Yeah, because you would have integrand is divergence, and this is D, like your whole entire region.
Right.
So it's the volume of it.
Okay.
So then you'd have that,
Mhm.
and that equals the flux of what you want to find, which is just the top part. So like what you want plus flux of the lid. Because this lid, we can use Stokes' theorem to find the flux of this lid part, which should be easier because it's a flat surface, just like we did earlier.
How would we, is it still circulation? That's not a curl, right? So then how would we find the flux into this?
Flux of let me see. Wait. So this is in. Oh wait, not this. So because you're still finding the flux of. Okay, I guess this is very. Wait, I have an explanation. So if you have some surface and you want to close it up by additivity, so like adding this lid, then we have that what we want. So this is the thing we want, which is non-closed, is going to equal this thing, which we can use Gauss's theorem, plus the thing we know how to compute. And how do we compute something like F dot ds? Well, F dot ds, according to the chart, F dot ds. Okay, wait, it's still using divergence theorem, perhaps.
It's like, how many flux is it have to be everything? Unless it's curl.
Let me. Okay, yeah. So you can still use divergence for this then, because now we have a 2D shape that's still closed. Wait, I feel like sorry. Let me think. Oops. Okay, so yeah, so still use divergence then. So this would most likely give you 0 most of the time. And so it's a minus. So you end up getting that the flux of what you want equals the flux of yeah, equals flux. So yeah, you can use divergence to find this thing, which is now easier because it's an flat surface, and we know the boundary, which is this circle, and then that would equal what we wanted to find, which is like an even harder surface. Like we don't know how to do this parabola thing. In the practice problem question number 2, it turns out our vector field, so like flux would be flux over some f. But in that practice problem, f is like the curl of something else, which is why we'd end up doing those to find this specific Yeah.
So why is the flux, the total flux, 0?
Usually it's 0 because like you have some, because you're doing like the divergence, and usually like some things, like when you do the divergence, it starts to cancel out and you end up getting 0 for most problems. But if it's not, then you just have something else. Like you have flux of total plus but usually the like problem is trying to hint to you that you need to use this, and so the total, like if you use divergence, you'll end up getting 0. But it doesn't have to be 0. I'm just saying it usually is.
So this is when you use like when you don't have something that's closed
Mm-hmm.
and you need to make it closed.
Yes. Yes.
But you could also just use you have to use this with another way to do it.
You might be able to use Stokes, but then that would be more work, right? The point of doing this is because divergence is easier to calculate. Like you'd probably get some number multiplied by the volume of your shape. So like if you have some non-closed shape, which is the top of this paraboloid, and we could just close it by finding this lid. Well, this lid is also easier to find too, as opposed to like a whole, like a complicated parabola. Okay, so let me do an example. This example actually shows you that like doing the divergence doesn't always give you 0, but like for these types of problems, it would usually happens that way. But say you wanted to find the flux of some unit cube. So you have a cube, this shape is closed, like there's no opening, it's a closed cube, and you're trying to find the flux outward. So we see that it's a closed shape, a cube, which means we probably want to use Gauss's theorem because it's closed. What does Gauss's theorem say? The integral of f dot ds is going to be, you do the triple integral over your region or your shape, where your integrand is the divergence. So what is our function? Our function is xy plus I plus yzj plus xvk. So what's the partial with respect to x of this first thing? That's y. Partial with respect to y of the second thing is z. Partial with respect to z of the last thing is x. And so we have this triple integral of y plus z plus x. For cubes, they tell us that x goes from 0 to 1, y from 0 to 1, z from 0 to 1. So the length of the sides of our cube are each 1. So we have 0 to 1, 0 to 1, 0 to 1. And if you compute that integral, you get 3 halves. Any questions on that? Okay. Let's see. Okay, so let me actually do this practice problem for you guys. I think was a little bit confusing. Okay, this is practice problem number 2. Okay, so I'll let you guys read the question first in case you haven't looked at it. Okay, so let me start us off. Okay. So first I'm gonna say that we have this vector field and we're told that it's the curl of something else. So F bar is the curl of something else, some other V. This vector field, so they tell us that S, our region, what we're looking at, is some paraboloid above the XY plane. So the shape that we're looking at right now is just the parabola itself. So just the top part. This tells you, and they don't say anything about it being closed or anything. This tells you that we have an unclosed shape. You just have the top part of your paraboloid. So it turns out that, well, what is something we could do to make things easier for ourselves? If we close that parabola, if we close it so that it has a lid, well, then we can use Gauss's theorem. Because for Gauss's theorem, we just need a closed shape and we could use the divergence. So if we close that lid, so close the lid. According to our formula, we have that the flux of like the total, I'm just gonna use flux total. So the closed shape, so closed shape is going to equal flux of what we want, which is the unclosed part, plus or minus flux of the lid, which is our supposedly nicer shape, nice shape, which is the lid. Yes.
Wouldn't we use Stokes for
Mhm.
F part, and then okay, so we use Stokes
Mhm.
F and Gauss for the
Mhm. Yeah. Yeah, I'll explain. Okay, so first thing we want to do. Oh wait, do people know how to find B? Wait, I forgot how I found B. How did I find B? Okay, wait. Let me first explain how to find B first. Okay. So F bar is a curl of some other vector field, right? So if F bar is the curl of some other vector field, then what happens if we take the divergence of a curl? Well, in the nice chart that I had, we know that divergence of curl equals 0. So I have divergence of curl equals 0. What is our F bar? Our F bar had like, F bar was by squared I plus 6y squared, or it was something else. What was F bar was bxy squared I plus 2y cubed plus 3xzj plus y squared z plus 6k. So if I take the divergence of this curl of the vector field, I get, what's the partial with respect to x? That's by squared. Partial with respect to y is 6y squared. Partial with respect to z is just y squared. So now I have that this divergence should equal 0, or I get by squared plus 7y squared equals 0. So how do I get it equal to 0? B should be -7. So I use this using the fact that I know capital F bar is some curl. The divergence of any curl should be 0. And so that's how I figure out B. Any questions on how I found B? Yes.
What did you say you listed out like all the processes?
Yeah, that's coming next. So first I just found B so that I know what my F bar is first. Okay, so now back to the question we had. So we want the flux of our total closed shape to equal the flux of what we want, which is the unclosed shape, minus the flux of this nicer shape, the lid. So first, how do I find the flux of this total shape? Well, it's closed, so we can use Gauss's theorem. So find the flux of total, use Gauss. And what does Gauss's theorem say? It says that the flux of curl of F is going to be the divergence of F dA. What is our divergence? Well, we saw that it was by squared or negative 7y squared plus 6y squared plus y squared dA, which gives you 0. So if we have this entire closed shape and you take the divergence or you're finding the flux, you get 0. Yeah.
Wait, the flux would curl.
Okay, maybe not flux. Flux of F.
But are you talking about, isn't flux of F the flux of the curl of V? And you
Should I maybe
are you finding the lid or are you finding like the ground?
the entire shape? So we're trying to calculate F dot ds right now. F dot ds of the entire shape, because the question says we're trying to find F dot n d sigma or F dot ds. And so from our thing, divergence theorem is F dot ds is the
But-
divergence.
Okay, wait, so how, okay, is it because the question is, wait, can you answer the question?
Mhm.
So if the question asks for the integral of V or whatever, or like the flux of V, you would have used Stokes on
Right.
F.
Right.
But since it's asking for the flux of F, we kind of, so like the only reason it told us it's a curl of something is that we could find the value of
B, yeah,
Okay, now we're just going through and doing like
the actual curve.
Gauss for both parts because it's just we're finding it only for F, the flux of F.
Well, the flux of the lid, we're gonna end up using Stokes.
Okay, yeah. So, but basically we're finding. Oh wait, why would we use Stokes if we're finding the flux? Again?
Because for Stokes, this part is gonna be like we're trying to find the flux of the curl itself. So like for the ones, each of the ones, we're trying to find flux of the curl because we're trying to find flux of capital F bar, and F bar is the curl of something.
Then why would we use Stokes?
So because if it says flux of the curl, we use Stokes.
We just said
But because now we have a closed shape, like we're finding the like net flux over this whole shape. So like with divergence, it's not so like I guess because it's now closed, we don't really it's a closed 3D shape now. Like how
I'm confused about two things.
Mhm.
The first thing I'm confused about is I thought when you were going over that, it's F dot ds. I thought we agreed that we use Gauss on every part for this example. The one before, the one where we were subtracting the finding. I thought we agreed that you use because it's F dot ds, which is divergence. So I thought we just said like 5 minutes ago, use Gauss on each part of that. And the second thing I'm confused on is the question is asking that we find the flux of F, right?
F
So-
bar, yes.
So does it matter that it's the curl of V? Like I thought we just said that.
So okay, wait, let me see. back to my solution.
Yes, the no part or whatever, like that's
Oh.
yes, which is Gauss.
Yes, yes. Okay, okay. Wait, let's use this definition, right? So I'm straight copying and pasting. My wording here might have been a little bad. Okay, this formula, right? This is our formula. So this part, I said we're using Gauss, which is we're doing Gauss on the entire shape. And this part, yes, it's Stokes. This part, yes, Stokes.
Why is it Stokes?
Because we're doing, because F right now, our F is F bar, and F bar is the curl of something else.
Right, but it's not Stokes.
I know this part is not using Stokes.
Okay, yeah, but Stokes says the curl of
The
the flux of the curl.
Mhm.
So, but it says the flux of the curl of F. So, like, doesn't Stokes only apply for the flux of the curl when you're trying to when everything's related to F itself? Like, it's the flux of the curl of F. But here,
You could say the flux of the curl of B.
yeah, but it's asking us to find the flux of F, right? Not V.
It's saying find F. It's saying to find the flux. This is finding flux of F bar. This formula is saying find the flux of F bar. Because what is
The flux of F bar has nothing to do with V though, right? So why would you treat it like the flux of the curl or something else? Now you're just treating F bar as its own. You see what I'm saying?
yeah, okay, so because I have it. So what is flux of okay, let me so right now we're trying to find flux of F bar. F bar is the curl of something. So and we're trying to find the flux of this whole like function now.
But that's only when you're finding the flux of F and you have the curl of F and you're integrating the curl, right?
Right. So now we're skipping the step where like they gave you F. Now we just have the curl.
Right, but it's gonna give us if we use divergence theorem or if we use Stokes on F, won't it give us the flux of V?
Flux of the curl of V. Stokes, if we're doing okay, so like where's my
give us
thing?
the flux of the curl, which is F, or yeah, okay. Sorry.
Yeah, so this is like F bar, and this would give us flux of F bar. But what is F bar? F bar is flux of V.
Flux of curl of V. Okay.
Yeah, sorry,
So we
flux of
use
curl.
Stokes on it.
Yeah. Okay, so this part, this had a lot of layers to it. But okay, so now we're at this part, right? So let's find the total divergence. Okay. Total divergence, we saw 0. Oh, question?
Yeah, why can't you just use Stokes for like the boundary bottom out?
But to find, but then you'd have to know V bar. Wait, that's what we're doing. We're gonna use those to find and use this boundary. It's what we're
Be the flux for the whole shape. You find the flux of the curl and like the inside shape is the boundary.
wait, yeah. Okay. That's the idea because So you're proposing that we just use this bound, the bottom boundary for Stokes, right?
Yeah.
The reason we can do that is because of this formula. This formula. So the reason we can just do what you're saying is because this formula says that if we did the divergence of the whole thing, we get 0. That's why I'm saying, like, usually the point of these problems is that our total will end up being 0, because then it just proves that we could have just taken just this curve and did Stokes, as you said, like just doing one integral. Because it turns out that if this total is 0, then this length, just calculating it like nicer, is going to equal what we actually want. Like, we don't want to use this whole like problem, right? So we want to do what you said we should do. And the reason it works is because it ends up that the flux of the whole closed shape, if we did the divergence theorem, would give us 0. Is that any questions on that? So we found that using Gauss, we get the whole thing is 0. And so then how do we want to use our circle. This is our nice shape. So that circle, so now we're finding this thing that we know, the easier shape, the nicer shape. By Stokes, it says that, so we're trying to find f dot dr, which Stokes says we could do the curl of f dot n d sigma. And then you can either use Green's theorem for this part, or let me continue with Stokes and show you why it's the same as Green's. Because what is our curl? Our curl is -7x squared 2y cubed plus 3xz y squared z plus 6. That's our curl, which was given in the questions. Maybe I should write curl of b, sorry. Okay, and n, if this is our flat circle, what is the normal vector? It's the k hat, which is 0, 0, 1. So I have dot 0, 0, 1 dA. And so we're left with, well, it doesn't matter what these terms were, because this times this is 0, this times this is 0. What do I get here? I have y squared z plus 6 times 1 dA. But what is z? Now that we're on the flat circle, we're on the z equals 0 plane. So if z is 0, that whole term becomes 0, and we're just left with the 6 here. So it becomes 6 dA, or 6 times the area of our circle. What is the area of our circle? Well, our circle was what, x squared plus y squared equals 4. So pi r squared, or 6 times 4 pi. So the final answer is 24 pi. And so it gives us that, what we just found, 24 pi. 24 pi equals the flux of what we were trying to find. Okay, so that was the final answer. Yes?
We have to see what I got between the vectors.
Know that they're like separate. Like you can't mix the different formulas. So if they give you something with one forms, like stay in one form. I think I have a case. It seems that Grace really likes one form, so maybe definitely know the one form definition. Yeah.
Is this the vector language?
Yes, this is the vector language.
But if we stay with forms, don't we do like wedges and stuff, like we won't be able to.
Yeah. So sometimes like vector notation, like if you get stuck with the one form language, vector notation actually like still works. Like a lot of people, I think in the Green's theorem problem or some other problems, maybe some people did parameterization or like vector language way, which actually made things like nicer. Or like,
Speech and speech.
yeah, as long as you translate it correctly.
Oh, yeah.
Okay, any other questions before I end?